here we go. Yeah, so the intention of my two talks today and on Friday is to give you a solid grounding in plant canopy airflow physics. And this, of course, is completely impossible, if not for you, certainly for me. So what I'm going to do instead is to give you a view of canopy airflow as a complex system. And complex systems have two critical properties. They're emergent and self-organizing. So emergent means that the whole is greater than the sum of the parts, which is a fairly trite thing to say, but nevertheless has some real meaning. And self-organizing means that they have some preferred states that they like to be in and will tend to drop into these states. Before I can even do that, though, I know that some of you are very familiar with turbulence and turbulent physics and boundary layers, but some of you are not. So I'm going to start with some very basic stuff on turbulence, and then some stuff on the atmospheric boundary layer. And then at the end of the first 40 minutes, we'll get into what happens as we get near canopies. And the second 40 minutes will be about what happens when we get inside canopies and just above them, and why it's different from all the stuff that I talked about in the first 40 minutes. So let's get going. I've put this list of contents up, not so much for you to read it now, but basically as a content list for, I guess these talks are going to be available on the web and so on, so you can use this as a mnemonic. So there we go. Let's start. The Earth's surface is in this Goldilocks position. You know, Goldilocks and the three bears, where the right porridge is not too hot, not too cold, but just right. So the surface of the Earth is at this Goldilocks point for carbon-based life forms. You know, we have liquid water, we have all the stuff that we need, and it's a balance of radiation in from the sun, shortwave radiation, long-wave radiation out, and the transfer of the heat that gets down to the surface from evaporation, latent heat, and sensible heat. And we'll be concentrating really on these two terms, the evaporation and the sensible heat terms, as they're modulated by life, biological life on the planet. So that biological life on the planet, on the land surface, fixes about 55 gigatons of carbon per year, roughly. That's a difficult figure to pin down. But about getting on for 40% of this is already appropriated by humans for food and fiber. So we rely pretty much on the amount of carbon that plants are fixing, the work that plants are doing for us. As Gabby said in his talk this morning, looking at the human population singularity, we're assuming that this singularity, as we approach it, can be fed. You know? So there are lots of things which will change that those parameters in that equation, and how much the planet can produce in terms of food and fiber is one of them. It's also a very limiting factor on some quite outlandish speculations that you often see in the climate world, or climate mitigation world, the possibility of using biofuels or biosequestration often runs against physical limits. The layer of the atmosphere closest to the ground, the layer that reacts to the diurnal cycle of heating and cooling as the sun comes up and goes down every day, is called the atmospheric boundary layer. And in the daytime, the atmospheric boundary layer is always turbulent. So these animations and all the others that I'll show, particularly in the second talk on Friday, are all the result of work by my colleague Ned Patton at National Center for Atmospheric Research in Boulder, Colorado. So in this case, we're looking at the temperature patterns in atmospheric boundary layer up to over 1,000 meters. And we're just seeing the top of the boundary layer in the near neutral case, where the thing is driven by wind, and in the free convection case, where things are driven entirely by buoyancy, the boundary layer is even deeper. We'll come back to say a lot more about this, except the critical point in terms of limits to life are that without turbulent mixing, the daytime temperature range will be much, much larger than it is now, our day and night temperature range, and the exchange of heat, moisture, CO2 for plants and respiration, dispersion of pollutants will not be possible. In fact, the boundary layer, instead of being of order kilometers deep, will be of order meters deep. And basically, we choke, freeze, starve, die in our own exhalations or whatever. So it's absolutely essential. So let's start by looking at turbulence. Turbulence is this chaotic, random movement of fluids when they're flowing. There are two kinds of turbulence pictured here. The one on the left is the emergence of turbulence in a smooth flow over a smooth surface. Actually, this is a smoke tunnel that was worked in Cambridge in the late 60s, early 70s by a guy called Mike Head, and this was his student Bandy Paddy who produced these pictures. And you used to be able to see this smooth flow of smoke across the bottom of the wind tunnel and wrap the side of the wind tunnel with your knuckles, and that bit of disturbance will be enough to produce a turbulent spot which will go down the tunnel. So that's driven by shear, one layer of air going faster than another. The other one you'd also be familiar with is buoyant turbulence. So that's just a plume from a candle made visible by an interferogram, and you see it starts off as a smooth laminar flow and then spontaneously becomes turbulent. So let's start with that first thing, shear turbulence. Shear turbulence occurs when layers of air of different speeds slide over one another. And because the air is sticky, if you feel the air, you can feel how sticky it is. It's got viscosity. It's like treacle, but not quite as trickly as treacle. It means that as one layer slides over another, the layer going faster will pull the layer going slower along, and the layer going slower will retard the one going faster. And if you imagine a lump of air, as we call it, the technical term for a parcel of air is a lump, the layer of air above is dragging it along by a viscous force, which we denote by viscosity, mu, times the gradient of the velocity. And below we have a smaller viscous force, because the air down there is going a bit slower. And so that gives you a couple. It tries to turn that parcel of air over. But there's a resistance to this, because as you accelerate the air and move it over, it will sort of react by having an inertial force which opposes the viscous force. So the viscous forces tend to amplify the flow perturbations. These inertial forces, which is pressure gradients and just inertia of air with finite mass moving or accelerating, the inertial forces damp them out. So if you had no viscosity, again, Gabby talked about the Euler equations this morning, which are the equations for flow with no viscosity. If you have no viscosity, then a boundary layer profile like that with steady increase in velocity won't go turbulent at all. So you can think of viscosity as a kind of a delaying thing, which means that the inertial force gets out of step with the pressure force, and things can sort of cascade out of control and become turbulent. And so the first proper descriptions of turbulence were down to Osborne Reynolds, who did a series of experiments in 1883. And he had a tube, I think it was liquid flow, and the tubes were actually vertical. They're usually portrayed on their sides. And he put in a stream of dye in this liquid flow and looked at what happened to that stream of dye as he increased the flow speed. And he found that at a certain speed and size, if you like, there was a transition from a smooth stream to a turbulent stream. You can do this yourself with a tap. Just turn the bathroom tap on, and you'll see that the water that comes out of the tap, if you don't turn it on too hard, is initially nice and smooth, and then it will go into a random term of thing. So Osborne Reynolds defined the Reynolds number as the ratio of inertial and viscous forces acting on the fluid element. So the inertial force is of order the density times the gradient of velocity, or the acceleration, spatial acceleration. So it's of order rho times the square of the velocity divided by a typical length scale of the flow. And the viscous force as the viscosity times the second derivative of the velocity, which is of order mu u on L squared. And if you take the ratio, you get the Reynolds number, which is the velocity times the typical scale of the flow. It will be the diameter in Reynolds experiments, divided by the kinematic viscosity, which is the ratio of the viscosity and density. Now we know the kinematic viscosity is a very small number, like 15 times 10 to the minus 6. And so this transition to turbulence occurs at Reynolds numbers somewhere between 2,000 and 12,000, depending on other factors. So in shear turbulence, we have layers of air of different speeds flowing over one another. We call it laminar flow because we're looking at laminae, sheets of air. Before the transition to turbulence, momentum is exchanged just by exchanging molecules. Now, molecules don't travel very far. The mean free path before it hits another molecule is very, very small. And so because there's such a huge scale separation between the distance over which the process transferring momentum, fast molecules going up, slow molecules coming down, such a large scale separation between that and the flow itself, you can regard the viscosity as a property of the fluid. Depends on the density, the temperature, maybe some chemical admixtures, but it's a property of the fluid, not a property of the flow itself. And we have this flux of momentum, which we also refer to as the shearing stress, between the faster moving lamina and the slower moving one below. And the flux of momentum in the laminar side is given directly by the viscosity times the gradient of velocity, the rate at which the velocity is changing across the flow. In turbulent flow, the adjacent laminae transfer momentum by sending macroscopic lumps of air between the fast and slow moving fluids. But in turbulent flow, the movement of these parcels or lumps or whatever I'm going to call them, I'll probably think of other nouns through this talk, is a consequence of the flow itself. And it's this actual nonlinear recursive property of turbulent flow that makes it so difficult to actually calculate, because the rate at which these parcels of air are exchanged depends on the flow itself. It's the rate of exchange of the parcels which determines the shape of the flow. Now, turbulence is much more efficient at exchanging momentum than molecular diffusion. So the eddy viscosity, the equivalent for a turbulent flow of the molecular viscosity, is 10 to 100,000 times larger in the atmosphere than the molecular viscosity. And that's why the boundary layer during the day can be kilometers deep. And if there were no turbulence and we relied on viscosity, it would just be a meter or two deep. So the natural state of the daytime boundary layer is fully turbulent because transition occurs around Reynolds numbers of around, of order 1,000 to 10,000. Atmospheric Reynolds numbers are about 1 million to 100 million. So the atmosphere is almost always fully turbulent, unless other things intervene. And we'll look at one of those next. In this picture, the turbulence is generated entirely by shear. So we have high and low pressure systems that you see on weather maps. In the high pressure system, the air is sort of driven towards the low pressure. There's a balance also with the fact that the Earth's spinning, the so-called Coriolis force, which is really just a change of reference frame, but nevertheless, the balance between those two results in the so-called geostrophic wind, which is in the non-turbulent part of the atmosphere above the boundary layer. And so we have a fast-moving airflow above, and then we have steadily slower layers moving down until the layer actually in contact with the ground is stopped, and that's the boundary layer. So a shear-driven boundary layer, we can see the faster-moving layers above and the slower-moving layers below. Now, buoyant turbulence, the candle flame picture, is a bit different. On the left-hand picture, you see an unstable density gradient. So the lighter air is below and the heavier air is above, and you immediately think that's got a tendency to turn over. That doesn't seem right. So if you displace a lump of air in that gradient, move it up a little bit, then the air that moves up will be slightly less dense than its surroundings because it's moving up into a more dense region. And so the buoyancy force will keep it accelerating. If you move it down, the lump of air will be more dense than its surroundings, so it will keep accelerating. So in an unstable mean density gradient, any small perturbation will expand. You remember Gabby's demonstration of small perturbation analysis this morning. In a stable density gradient, where the heavy air is at the bottom and the light air is above, then if you move a parcel of air upwards, it will be heavier than its surroundings and will tend to go back to where it came from. If you push it down, it will be lighter and will be pushed up to where it came from. So on that side, perturbations are damped out. On the unstable side, where density increases with height, perturbations are amplified. So when we look at the transition from laminar to turbulent flow in buoyancy-driven turbulence, we can do what the Reynolds did, and we can compare the buoyancy force with the slowing down action of viscosity. So the buoyancy force involves G upon T naught. G is the acceleration of gravity. T naught is a reference temperature in degrees absolute, degrees Kelvin, so probably 300 degrees outside here, 300 K. And delta T is the temperature perturbation. I could have done this in density, but it's more conventional to do this in temperature. You can basically switch temperature and density in the lower atmosphere, just add a minus sign. So the buoyancy force is given by G upon T naught, the small perturbation in temperature, a volume, which gives you the force, and then we have to put in the square of the viscosity. I won't go through the derivation of this, except to say that the critical Grashof number, where the flow will, let's say you had a vertical plate and you heated it, and you let the turbulence build up around it, then it will go from laminar to turbulent when the Grashof number is about 10 to the 8. Grashof numbers in the atmosphere are typically 10 to the 9 or more, but the more important number is the Rayleigh number. If you have a lump of air which is of different temperature to its surroundings, as well as the viscosity is tending to slow it down if it starts to accelerate upwards in a density gradient, you'll also have conductivity smoothing out the temperature difference. So the Rayleigh number involves a Grashof number modified for the fact that conductivity, molecular conductivity, is smearing out the temperature differences that were causing the buoyant acceleration in the first place. And in atmospheric boundary flows, the Rayleigh number is more important, as we'll see on Friday, actually. It tells us when buoyant convection will begin. The critical Rayleigh number is around 1,000. In the atmosphere, the actual Rayleigh number is about 10 to the 9. So if the atmosphere is unstably stratified, then it will also always have some buoyant turbulence augmenting the shear turbulence. So this is the other picture of the atmospheric boundary layer simulation by Ned Patton. And now we see that instead of the higher levels moving faster, the thing is still fully turbulent, but it's fully turbulent because buoyant plumes from the surface warmed by the sun are rising and cooler air is descending to replace it. So the normal state of the atmosphere during the day is to have two kinds of turbulence. One generated by shear, as a geostrophic wind drags the upper layers across and the contact with the ground slows them down, but also buoyancy, as the sun warms the surface and the air in contact with the ground warms and rises, and cooler air drops to replace it. So we're interested in the balance between turbulence generated by shear and turbulence generated by buoyancy. And we express this through a dimensionless number called the Richardson number. If you read some of the pre-reading stuff, you'll have got some familiarity with dimensional analysis and groups. So we can look at the time scale of a turbulent eddy growth through shear, and we can take that as the inverse of the velocity gradient. We can look at the frequency of the oscillation of an air parcel in a density gradient. So if we're in the stable side and we give our air parcel a push and let it go, then it will sort of oscillate and come back down to where it started, but it will overshoot a bit to begin with. And we can look at that frequency of oscillation, and it's called the Brandt-Weissler frequency. When things are stable, then the Brandt-Weissler frequency is positive. When things are unstable and things just diverge, the Brandt-Weissler frequency is imaginary. But we can take the ratio of the square of the Brandt-Weissler frequency, which is a real number again, and divide it by the timescale of turbulence eddy growth squared and get a number called the Richardson number, which tells us which dominates, shear-driven turbulence or buoyancy-driven turbulence. Now, if the thing is unstable, the buoyancy-produced turbulence augments the shear-produced turbulence. If things are stable, then the buoyancy-driven turbulence can damp out the shear-driven turbulence. And that's what happens at night in the boundary layer. And that's why the boundary layer at night, instead of being kilometers deep, collapses to 100 meters or a couple of 100 meters deep, because the turbulence has been squashed by buoyancy. One final thing, this is a very quick tour of turbulence. The ultimate fate of the turbulence energy, whether it's produced by shear or by buoyancy, is to end up as heat. And it's dissipated by molecular mixing at a very fine scale. So we get big eddies, you saw some of them in those pictures, and the big eddies drag each other apart and produce layers of high shear. These do the same with their neighbors, and eventually you get layers of order a millimeter deep. And in those layers of a millimeter deep, viscosity, if you like, can grab the energy and damp it out and exchange it for heat. In the same way, differences in density can be smeared out by conductivity, and again, the ultimate result of that is heat. So we inject energy in what we call the energy-containing scales of turbulence. It gets passed from eddy to eddy, smaller and smaller, and then it gets dissipated to heat. There's a little rhyme which goes back to Lewis Fry Richardson, one of the famous meteorologists of the 20s. And if I remember, it says something like, big whirls have little whirls that feed on their velocity, and little whirls have little whirls, and so on to viscosity. So if you remember that, all you need to know about the eddy cascade. So that's turbulence. What about boundary layers? Well, if we have a boundary layer on an object, let's say an aircraft wing, we begin with a laminar boundary layer because the distance is very small along the wing, and to begin with, we don't exceed the critical Reynolds number for turbulence. But very soon we do. We end up this transition region where we go from laminar to turbulent. Then we have a fully turbulent boundary layer. In the atmosphere, you can forget the first two parts. It's turbulent almost all the time. And the boundary layer is right down the bottom here in the layers of the atmosphere. We have this relatively deep thermosphere where the main characteristic of the thermosphere is it interferes with radiation, but there's almost no air in there. The mesosphere, still pretty lacking in air. Stratosphere, you wouldn't want to breathe in it. The troposphere, the bottom few kilometers, and the atmospheric boundary layer that's responding daily to the rising and setting of the sun is just the bottom couple of kilometers. Then we're going to be particularly interested in the surface boundary layer, because that's where we generally live, where plants grow, and so on. And if we track the growth of the boundary layer through the day, let's start at sunrise, the boundary layer grows very quickly through the morning, up to its 1 to 3 kilometers height. These are sort of mid-latitude boundary layers, and it carries on like that until sunset. And then by a mechanism we won't have time to go into, the boundary layer collapses, or the turbulence collapses very quickly in half an hour. And from being sort of 3 kilometers deep and fully turbulent, it goes to being 100 meters deep and stably stratified, but still turbulent. And in between, in that sort of 2.8 kilometers, there's all this sort of remnant fossil turbulence that rattles around during the night and generates waves and stuff. It can be quite complicated. If we take a picture of this is with an acoustic sounder, fires sort of a sound radar. It fires pulses of sound into the atmosphere. These get reflected from fluctuations in refractive index, and you can pick them up again. And you can see the structure of the boundary layer. You can see the growth of the boundary layer in the morning, and then it reaches this kind of equilibrium. As it starts to hit against the stably stratified air higher up in the troposphere. And you can see the interface between the turbulent and the non-turbulent parts of the boundary layer. It's actually very, very thin it's of order millimeters, a thing called the Kolmogorov microscale. But its actual up and down motion can be 20% of the boundary layer depth. To tell you a funny story about these acoustic sounders, to give these beeps, and we were using one at an experiment looking at the dispersion of smoke from a power station on the coast of New South Wales coast, about 100 kilometers north of Sydney. And we had this acoustic sounder in this fairly swampy ground east of this sharp escarpment, and it was beeping away, and we were getting all these strange echoes, and particularly at sunset. And we went out one night at sunset, and around the acoustic sounder was this circle of frogs. And every time the radar went beep, the frogs went rivet, rivet. These crazy echoes on the... So, perils of acoustic sounders. So we're interested, as I said, in the surface layer, which is about 100 meters deep. Above, in the whole atmospheric boundary layer, kilometer to 3 kilometers deep, we have much larger scale turbulent eddies. You saw some of them in those pictures. And we'll talk a little bit more about how we describe them. But first of all, some basic concepts about turbulence that we're going to use over and over again. We usually refer our turbulent velocities to axes. X is along the direction of the mean wind, the time average wind. Z is usually vertical in the direction of gravity, and Y is in the third direction. Usually use a right-handed coordinate system. So that's X, that's Y, and that's Z up. Average covariances between fluctuations in concentration or in wind speed can be interpreted as stresses or scalar fluxes. So momentum flux or shearing stress, if on average every time the wind's fluctuating is down, the wind speed is a bit higher, then you'll get a transfer of momentum towards the ground. If on average every time the wind speed is up, the air is a little bit warmer, then you'll tend to get a transfer of heat upwards. If every time the wind speed is up, the water vapor content is higher, then you'll be moving water vapor upwards. So these covariances, the average products of fluctuations in velocity, in temperature and vertical velocity, humidity and vertical velocity, are called fluxes and stresses. And a lot of what we're going to do in the next little while is about these sometimes called mythical, horizontally homogeneous steady conditions, because it makes life a lot easier. So it's very hard to find any of that around here, with that mountain in the way. But expeditions went to the far corners of the Earth to find the 2 or 3 places on the entire planet where things actually matched the theoretical deductions of boundary layer meteorology. And we'll look at one of those things soon. But in steady, horizontally homogeneous conditions, all of these things are constant, pretty much constant with height in the lowest 100 meters of the atmosphere. And we rely on that in a lot of our analysis. And remember, I introduced those eddy diffusivities in analogy with the molecular diffusivity. So we have one for momentum, Km, one for heat, K theta, and you can write one for humidity too. And I'll put a warning early on that unlike the molecular diffusivities, which are properties of the fluid, the eddy diffusivities should only be used when they're supported by similarity analysis. There are sort of physical arguments for how they appear, and I'll show you some of them, but really don't trust them unless there's similarity analysis behind it. So the daytime atmospheric boundary layer, I showed you a couple of pictures. The interfacial layer, 20% or so. In reality, the interface between the turbulent region here and the troposphere here is that thick, but in fact it's going up and down all the time, so we have this interfacial layer. The temperature increases with height in the troposphere, so it's stable. The surface gets heated by the sun, and the temperature then drops as you go higher, so it gets more dense. So we have an unstable layer near the surface. Then the eddies are so energetic in this mixed layer that there's basically any variation in temperature with height gets mixed out. We have up here a balance between the Coriolis and pressure forces, which determine the direction of the wind speed. Down near the ground, we have a balance between the pressure gradient and the drag of the ground, and the wind can change its direction from the top of the boundary layer to the bottom. It's called the Ekman spiral. And we get variations in the shearing stresses for both the streamwise. If we align our coordinates with the direction of the wind at the ground, then the wind at the top of the boundary layer may not be pointing in the same direction. So we transfer both V and U momentum towards the ground. And we can do some scaling. We can look at that and we can say, what are the important things which might determine any of the properties we want to measure or calculate in this whole boundary layer? And the distance from the ground seems pretty important. The depth of the boundary layer is probably important. The friction of the wind on the ground, which is what's causing the whole thing to have a boundary layer, in a sense, ought to be important. And as we said, the correlation of the wind speed, fluctuations in the streamwise and vertical wind speed are transferring momentum towards the ground. It gets absorbed as drag on the surface. It's going down, and our z coordinate is positive upwards. So if it's going down, it's negative. So we multiply, if we give it a minus sign, so that quantity is positive, and take its square root, we've got something with the dimensions of velocity. Remember, UW is constant through the bottom layer, so we can take that as a sort of a scale for whatever's causing the wind speed to depart from being uniform because of drag on the ground. And the other thing that's important is the heat flux from the surface, as the sun hits the surface. And we can take all those scales and form a velocity scale called W star. We can find that if you look at that, you'll see that it involves this buoyancy parameter, G upon T naught, the heat flux from the ground, the depth of the boundary layer, and that's some characteristic velocity scale for these very large energetic eddies in the mixed middle of the thing. I didn't show you how you do that, but I'm going to do that this very quickly for the surface layer. There's a thing called Buckingham's pi theorem, which some of you will have heard of. If you haven't, at some point you're going to have to encounter it in your careers. And it's a bit of an arcane thing, but it's actually very important for if you've got a problem to sort of figure out what the problem might depend on, how it's best to sort of arrange your data, arrange your formula, try to understand how one thing depends on another. And it says, it looks like gobbledygook, if you can identify m-1 parameters governing, let's say you've got the dependent variable you're interested in. It might be rate of cavitation in plants, it might be the heat flux from the surface, it might be the velocity gradient. And you can identify the m-1 parameters that govern that, and I give you a list for the mixed layer. And if you've got n dimensions represented by the variable and its parameters, it might be length, time, temperature, and so on, then you can say three things. There'll be m-n independent dimensionless quantities you can make, and the non-dimensionalization is done with the parameters. An independent quantity is one that can't be made from the others, and these quantities will be functionally related. And I'd recommend the book by John Wingard, published in 2010 on turbulence and the atmospheric boundary layer for a good introduction to this. But let's just try it on the atmospheric surface layer, this layer just above the canopy part that we are interested in particularly. So we can identify, how many have I got there? 4 parameters. Distance from the ground, obviously that's going to be important. U star, this friction velocity, it characterizes the drag of the surface, that's going to be important. The heat flux we assume is important, and this buoyancy parameter. So there's 4 parameters there. 4 parameters, m-1 is 4, so m is 5. There are 3 dimensions. There's length, time, and temperature. So n's 3. So that means there are 2 independent dimensionless groups you can form. So it's conventional to take one of these groups as the thing you're interested in and make it dimensionless with the parameters. So let's assume we're interested in the velocity gradient, du by dz. So we make the velocity gradient dimensionless with u star and z. Then the other dimensionless group is conventionally taken as z upon L. Now, L is called the Obukhov length, and it was postulated by this well-known or famous Russian physicist Obukhov, and I think it was widely promulgated in the paper by Monin-Obukhov. Is that the right one, Gabby? If you want to read about this in more detail, the best textbook is one by Monin and Uglom, which is still in print, I understand. So what the pi theorem tells you is that if you make a quantity like the gradient dimensionless with the other quantities, and I'll tell you what that little kappa is in a minute, then it will be a universal function of the other dimensionless ratio, z upon L. Same thing goes to the temperature gradient. The dimensionless function, the functional form, the pi theorem can't tell you anything about that. You've got to find that by other means. But it's still a major step forward. And it's actually amazing how far Monin and Uglom and Monin-Obukhov got with this with very little experimental evidence. So let's imagine that this surface heat flux is weak or negligible to start with, so strong winds near the ground. Now there are only two scales because Q0, the temperature flux, or the buoyancy flux is 0, and the buoyancy parameter is unimportant. So now there's only n-1 independent dimensionless group. It can't be a function of any other dimensionless group because there aren't any. So it's a function of nothing. In other words, it's a constant. So the wind speed gradient has got to take the form z upon u star du dz is a constant. And that constant is conventionally taken as k, which is a value of about 0.4, and that's called von Karman's constant. And if we integrate that little equation, z on u star du dz equals k, then we get the famous logarithmic law that the wind speed, as you move away from the ground, increases like the logarithm of the distance from the ground. And z0 is an integration constant which characterizes how efficient the ground is at absorbing momentum. So I've called it the ubiquitous log law because it sort of appears all over the place in boundary layer fluid mechanics. So again, if you take the log law there, well done, that should have been k. I've made a error there. So z upon u star du dz equals k. Integrate that and you get the log law. A physical, that's what the log law looks like. That's what the velocity profile looks like. The gradient of velocity increases as you get closer to the ground. And the physical explanation for that is that the eddies that are responsible for the transport, in the sense that the passing momentum, mean momentum from one level to the next, they're getting smaller as they get close to the ground because the ground is blocking them. They've got to be three-dimensional, and so you've got to have a bit of space between where the top of the eddy and the ground. As you get close to the ground, they get smaller. So if they've got to pass the same amount of momentum, because the shear stress is constant with height, then the difference in momentum has got to increase as the eddies get smaller. So you've got to have that increase in shear as you get closer to the ground. So when we do the pi theorem on with those inertial sublayer, surface layer parameters, we get these dimensionless groups. The dimensionless velocity gradient is phi m, and the function of z upon L. Temperature gradient is phi h, function of z upon L. That's the definition of z upon L, and that's got a physical meaning too. It's actually the ratio of the rate of production of turbulent kinetic energy by buoyancy to that by shear. And theta star is also conventionally created from the buoyancy flux just by dividing it by u star. And we add a minus sign because of the direction that the buoyancy flux goes. So as I said, all of this works if the atmospheric flow is steady, horizontally homogeneous, so it's not accelerating, decelerating. There are no sources and sinks of momentum or anything else in there. And people have gone to, far western New South Wales, to Deniliquin, and to Kansas. And in 1968, the Air Force Cambridge Research Labs from Cambridge, Massachusetts, conducted the famous Kansas experiment. And again, there's some very funny stories about this. My old friend Dwayne Haugen led the experiment, and they were looking all over Kansas for this perfect flat site. And they found the perfect place, which was owned by this old farmer and his sons. And the farmer hated the government. He wasn't going to let the government on his land. The sons were all for it because they were going to get a lot of money while they put some towers in the corner of a paddock. And Duane says that the farmer had 2 responses to requests to have the experiment. One was no, and the other was hell no. Anyway, they just about got an alternative site which wasn't as good when they got a phone call from one of the sons that the old bugger's dead. You can come. So the Kansas experiment ended up where it was because the guy just died in time. So we have the dimensionless 5 functions again, and a series of data, probably only about 2 weeks of data, produced these forms for the 5 functions. As I said, dimensionless analysis, the pi theorem won't tell you what they are. You've actually got to do experiments or do some more detailed analysis, which has actually taken about 50 years to appear. And Gabi and a series of collaborators have produced a wonderful series of papers in recent times, which actually puts these on a sound theoretical basis. But they have that form that the phi function for momentum, on the unstable side, that's to the left of the line, z upon L is like the Richardson number. If it's negative, it means that buoyancy is adding to the shear turbulence. If it's positive, buoyancy is suppressing the shear turbulence. On the unstable side, it goes like 1 minus alpha 1 to the minus a quarter, that funny shape. The heat flux phi function is similar with a minus a half, and the values for alpha 1 and alpha 2 are subject to a lot of argument, and people do different experiments in different places and come up with different numbers. As I said, k equals 0.4 is included in all those formulas to make sure that the phi function is 1 when z upon L is 0. If we plot the velocity against z on a log scale, so it's velocity against log z, remember plotting the log law, LMO is just Monin-Obukhov length, I should have changed that. Then we see that the stability effects are such that the neutral log law, which is a straight line, in the unstable case where we've got more turbulence, then the mixing causes the velocity profile to be fuller, and on the stable side, it becomes sort of sharper. And again, the physical interpretation is, in neutral conditions, it's a proximity to the ground, which means that the eddies get smaller and smaller, and so the difference in velocity between 2 levels has to get higher and higher. If the eddies are unstable, they're sort of stretched in the vertical, the more efficient at taking momentum from here to here, then you don't need as big a gradient, so you have that kind of shape. If it's stable, then the suppressing effect of buoyancy makes the eddies sort of less efficient at moving stuff from place to place, so the gradient has to get higher. And that's what it looks like if we plot it on log coordinates on the bottom right. So to finish this first part, so far I haven't talked about canopies at all. And what we'll do next is talk about canopies. So I'll leave you with just the difference the adjustment you have to make to the log law when you move from flow over a flat surface where all the momentum is absorbed at the plane to a canopy, which could be a forest or a crop or a city even, where the momentum's absorbed over some height range. And if you're up here in the inertial sublayer, where we still have all of these scaling parameters we've just introduced, so you're assuming you're not interested in the details of canopy flow, you're well away from the canopy, just regard it as a surface, then you've got to behave as if the momentum is being absorbed not at the ground, but at some kind of so-called displacement height, which is effectively the centroid of the drag on the plants. So we've replaced the form of the logarithmic velocity profile that I showed you before with a new profile where we change the coordinates. So Z, instead of being starting on the ground, now starts at this displacement height, which is somewhere in the middle of the trees. Okay, so we left it by looking at what happened as we get, when we make the turbulence more energetic by adding buoyancy, then we don't need as steep a gradient to transfer the flux of momentum or the flux of heat to and from the ground. But if you look at what happens as we get very close to the canopy, 2 or 3 canopy heights, but it's neutrally stratified, so we would expect to have the proper log law. In fact, what we see is the same thing as if we had buoyancy, that the actual gradient, these are measured in logarithmic coordinates, temperature and velocity, that the gradients are actually not as steep as they would be if they conform to the real log law, which is the dotted line. So somehow or other, as we get close to the canopy, the eddies which are doing the transfer are a bit more efficient than the log law assumptions would suggest. So let's have a look at the scaling just above the canopy, just reprising what we just did. So well above the canopy in the inertial sublayer, or the surface layer, we follow Monin-Obukhov similarity theory, or MOST. We have, just be a little bit carefully, the displacement height is conventionally measured from the ground up, but in dense canopies, it's actually mathematically more convenient to measure it from the top down and make the origin of coordinates the top of the canopy. But then either way, we have to change the origin of coordinates to the virtual origin. In this case, I've added a displacement height. And we have a phi function which depends on Z, now a new Z, relative to the virtual origin, and the Obukhov length, and so we go. And the length scale is now the distance from the virtual surface, the velocity scale is still U star, and we get the velocity, the log profile when we integrate all this. Now, what happens if we go in the canopy? Now we've got something different, because now we're absorbing momentum on all the foliage. So within a horizontally homogeneous, again, this mythical landscape, homogeneous dense canopy, dense meaning that all the momentum gets absorbed before it actually reaches the soil. It's all absorbed by the foliage. We can say that the drag, we can parameterize it as equal to the square of the velocity divided by a length scale LC, and LC is given by a drag coefficient times the leaf area per unit volume of space in the canopy. And we'll, in a couple of slides, we'll talk about how we got to that formula for the drag, but just stick with it for the moment. And U is now the horizontally averaged wind speed, which sort of takes account of the fact that the wind is now finding its way around the solid plant parts as well as being unsteady in time. So the velocity scale is still U star. If we assume sort of the momentum getting into the top of the canopy is still given by U star, if we assume that CDA is constant or LC is constant, then we can do, again, our dimensional analysis with the Buckingham pi theorem, and we get a formula for the velocity profile, which says that the velocity in the canopy decreases exponentially as we descend into the canopy. Physically, what's happening, of course, is because the momentum is absorbed according to U squared, the wind gets absorbed very quickly in the top of the canopy, and as it slows down, the momentum absorption gets less efficient. The mixing by the eddies is now constant. The eddies are staying the same size because we've made that assumption that there's only one length scale, and we produce this exponential profile. Now, here's a bit of a paradox. If we take the log law above the canopy and the exponential profile within the canopy, and we match them, and we make some sort of fairly sensible matching conditions that the velocity is continuous and the transfer of momentum is continuous through the top of the canopy, and we get a matching, we find out that the ratio of the friction velocity, the transfer momentum divided by the, or U star, divided by the wind speed at the top of the canopy is exactly 0.2, half of von Karman's constant. But observations over many, many canopies tell us that that number is really about 0.3. So what's happened? It's if we look again at our eddy diffusivity formula from the Monin-Obukhov similarity theory in neutral conditions, the eddy diffusivity for momentum is k, z, that should be z minus d now, u star, u, and then the gradient, that tells us how fast momentum is being transferred. Same for heat flux. It's sort of saying that this length scale z is too small. The diffusivity is actually larger than this formula predicts. So here are the length scales for, they're taken from spectra. The length scale sort of falls linearly as we get near to the canopy, according to Monin-Obukhov similarity theory, matches the data. These are Kansas data and some other data. But then as we get down into the canopy, it stops falling. The length scale that's controlling the eddies stops decreasing with height. The ground's not blocking them anymore. Instead, it approaches a constant value, so that the eddy diffusivities stop falling, and so you can get away with a less than logarithmic gradient in wind speed, less than logarithmic gradient in heat flux, and still transfer the same amount of heat or momentum. So this layer, where you depart from Monin-Obukhov theory, is called the roughness sublayer. And it's been recognized for a long time, because if you don't do this, then if you parameterize exchange from the surface into the boundary layer as if it was all Monin-Obukhov all the way down to the canopy, then climate models and weather models just go wrong. And the reason is that to get the right amount of mixing and drag and flux in the boundary layer, you have to make the surface look rougher than it should be, to accommodate that fact that the length scales stop falling. But if you do that, then you make all the rest of the boundary layer too turbulent and too mixy. So chemicals get diluted too much, the boundary layer grows too fast. So empirically, there have been many formulae to put in to represent the roughness sublayer. They all assume that you know what the depth of the roughness sublayer is. A few years ago, Ian Harmon and I proposed a new form of the roughness sublayer, which is based on some actual dynamical theory that we'll talk about in much more detail on Friday. But it says that there's a new length scale. So instead of the eddies being related just to the distance from the ground, or in the distance from a displacement height, there's a new length scale added in now, which is the vorticity thickness. And I'll tell you what that is in a little while. The vorticity thickness then means we have another parameter in our Buckingham pi theory. We have now an extra dimensionless group we can form, as well as the phi based upon z upon L. We can now have a phi, another phi, we call the roughness sublayer phi, based on z upon the vorticity thickness. So even in neutral conditions, we have this new phi. We usually put a little hat on it to distinguish it from the conventional Monin-Obukhov phis. And this is the vorticity thickness. And so if that phi function is less than 1, then the diffusivity, the eddy diffusivity, is increased to a higher value than Monin-Obukhov theory would predict. And this works. Here's just 3 examples from our flux station near Tumbarumba in New South Wales, west of Canberra. You often refer to as Tumba Bloody Rumba because there's a song about it. So maybe tell you about when I have a beer. But the black lines here are what Monin-Obukhov theory would predict, and these lines here are what the new roughness sublayer theory predicts, and it goes through pretty much the points, certainly in the upper canopy. And we're looking at increasingly unstable profiles. So we have a theory, and it seems to work. It corrects Monin-Obukhov theory. It works for a range of canopy densities. It stops working when the atmosphere gets too unstable and when it gets too stable. And again, we'll talk about that on Friday. So, okay, so far we've just talked about the large-scale stuff, the mixed layer, the inertial sublayer, or the surface layer. What happens when you get near the canopy? The fact that the large eddies which are doing the transport now stop falling in size. But probably time to look at what the canopy is made of, which is leaves and twigs and stems and branches. Early studies about canopies, when I got into this field in the early 70s, were based on these implicit ideas that canopy flow was actually boundary layer flow, not standard log flow, plus a lot of wakes from these twigs and branches added to it. And so there was a lot of work focused on the properties of individual leaves under the unstated and that assumption. And it was a sort of a cottage industry. People would put single leaves in the wind tunnel and measure its properties, and then they put 2 or 3 leaves or a whole branch in the wind tunnel. And the idea is sort of that you can build up a canopy from all the parts. But as we are going to see, the dominant turbulent structure in the canopy is a property of the whole canopy, not just adding together lots of little twigs and their wakes, the turbulent wakes. So then multi-scale interactions occur between what's happening at this scale and what happens in the whole canopy. So let's look first at the aerodynamic drag. How does that drag get absorbed on the canopy elements? So it's absorbed as aerodynamic drag on the foliage. The wind hits the foliage and it slows down. And there are 2 ways in which momentum is transferred to the foliage. First is pressure drag. The pressure on the front, blow hard on something, the pressure at the front of the object is higher than the pressure at the back, and there's a force. And pressure drag scales like the density times the frontal area, AF, of the object, times the square of the wind speed. But also there's viscous drag. We looked at the one laminar of air dragging on another. Well, one laminar of air will also drag on a solid surface. And that stickiness, that viscosity, gives us viscous drag. Now, viscous drag varies like the density again, but now the wetted area, not the frontal area, but the area that's subjected to air flowing over it, and times the velocity, not the square of the velocity. So we usually parameterize all the foliage drag as if it was pressure drag, because at the kind of Reynolds numbers that we find in the open air, the leaf Reynolds number values typical of the upper canopy suggest that pressure drag dominates. But of course, the canopy has an exponential profile, and in the lower canopy, the actual Reynolds numbers of individual leaves can be quite low. So there's always a viscous drag term as well. So if we write here, I've got some pictures. If we look at a circular cylinder, for example, then if we, let me go back to this. If we parameterize all the foliage drag as it was pressure drag for the reasons I just said, so we can write that the drag is equal to the density times the frontal area times the universal drag coefficient times the square of the wind speed. And this universal drag coefficient, a dimensionless number, is usually assumed to be a function of the geometry. But because we've actually got a mixture of viscous and pressure drag, there's some residual dependence on the wind speed in the drag coefficient. So if the wind speed is low, then the drag coefficient, because we've made things dimensionless with the square of the wind speed, will appear to climb. So here we are at low Reynolds numbers. The drag of a circular cylinder drag coefficient is very high, and then it drops. And when we get down to the regions where pressure drag dominates, then it's around 1. And then if the boundary layers on the object become turbulent, it drops again. This CD here is defined with a half in front of the row, and that's the way aerodynamicists usually do it. In canopy work, we tend to leave the half out. So our CDs are usually half the size of those you'll read in an aerodynamics textbook. So flat plates too, flat plates are all pressure drag, so they have a CD of about 1. Streamlined objects, which might be leaves, they have this dependence on wind speed or on Reynolds number, way down to Reynolds numbers typical of leaves well up in the canopy. So we do have a mixture of viscous and pressure drag. If the wind speed changes, then the drag coefficient changes, and it's often put down as streamlining, which is, there's actually not a great deal of evidence for streamlining in real canopies, except in aquatic canopies. If you look at work done by, for example, Professor Heidi Neff at MIT, where she looks at flow past water weeds and seagrass and so on, then certainly streamlining occurs there. But in forest canopies and that, not so much. What does happen is, as the wind speed decreases, then more of the canopy, because of the exponential profile, more of the canopy has leaves in the region where they've got more viscous drag than they would otherwise have, and so the drag coefficient appears to rise. It's not as much drag, but the coefficient appears to rise. So you can be very confused about that. Now, the other thing, the scalar exchange goes on. Every leaf has an energy balance. So we can write the energy balance down here as the net radiation on the leaf, which is a short plus long wave arriving at the leaf surface, minus the long wave radiated back out, the Stefan-Boltzmann law. And that's got to be equal to the cooling or warming of the leaf, which is usually quite small for a leaf because it's pretty thin. But it can be important if you're looking at forests and you've got to take account of trunks and big branches. Then the sensible heat and the latent heat. So these two terms typically over the day balance the net radiation. Now we also, at the leaf level, typically parameterize these things as the heat flux, as a temperature difference. Actually, I should have a length scale in here, but never mind for the moment. The difference between the leaf surface and the canopy, the average air temperature in the canopy, divided by a boundary layer conductance, which describes the difficulty of heat getting through the thin laminar boundary layer, molecular boundary layer on the surface of the leaf into the well-mixed canopy air. Now, momentum can be transferred both by pressure and by viscosity. Heat or other scalars can only be transferred by molecular motion. So the efficiency of transfer of scalars is typically 10% of the efficiency of transfer of momentum. It can be expressed as a thing called the Leaf-Stanton number, which is about 0.1. Now, the same thing occurs for the water vapor loss from the leaf, the evaporation. The leaf surface value minus the average canopy value divided by a boundary layer resistance. These two are slightly different because the conductivity of water vapor and heat in air is a little bit different, but they're often made the same just for convenience. And also, as we learned from the two talks earlier today, the water vapor arrives at the dry leaf surface through the stomata. And these are openings to the mesophyll tissue, which can be assumed to be saturated at the leaf temperature. So we often combine that statement with that one and write that the evaporation from the leaf is equal to the difference between the saturated vapor pressure at the leaf temperature minus the canopy vapor pressure divided by the sum of the two resistances, one through the leaf boundary layer, and then usually a larger one as the molecules get out through the tiny stomatal pores. Now, the canopy airspace, so far we haven't said much about the fact that it's a very complicated topological space. So long before people looked at this in real detail, they actually used to write the aerodynamic drag of the canopy as a body force. So they imagined that the air is moving through the canopy, it's exerting drag forces on all the leaves, so it's being slowed down. So it makes obvious sense to take the equation for momentum. So this is the equation for the balance of average wind speed through the canopy, parallel to the mean wind speed. It's got a pressure gradient, which near the ground you can usually ignore. It's got the stress gradient, the vertical gradient of the momentum flux, U prime, W prime, and add an aerodynamic drag. Why not? So the aerodynamic drag term is an obvious thing to write. Now, Alistair Tom and others, Joe Landsberg and people in the late 60s showed that in natural plant canopies, the drag is mainly pressure drag. So do what we just did, just as the aerodynamicists do, and write the drag force on the air as the density, the leaf area per unit volume, a drag coefficient, square the wind speed. But when we got fast response sensors like sonic anemometers, which can track very fast fluctuations in wind speed by bouncing sound pulses around a closed path, you could measure things like the shearing stress directly, these covariances. Problems start to appear with this parameterization, because if you can measure the second moments, the products of fluctuations, it becomes natural to write an equation for them. So you can write an equation for the products of fluctuations in the form of turbulent kinetic energy. When you do that, so this is the product of squares of fluctuations in the streamwise direction, that drag coefficient appears in the new equation as a damping term. It's as if it's squashing the appearance of turbulence. But in fact, common sense tells you, and measurements, that as the wind blows through the canopy, all the wakes and eddies from the individual plants are adding to the turbulence, not squashing it out. And that whole thing, that whole problem was a problem that was sort of one of these nasty little secrets that was banging along in the background of canopy turbulence and micrometeorology for many years. And it was resolved by a seminal paper by Roger Shaw and student Wilson. There's a very well-known micrometeorologist called John Wilson, and it's not that Wilson. This is, I can't remember that Wilson's first name. I don't think he carried on in turbulence. But they show that when you write the aerodynamic drag as a body force, what you've actually done is implicitly average over all the plants. And you've averaged over a multiply connected space, because this earth space you've averaged over has got all these solid bits, all these holes in, really, where the air can't go. And that has mathematical consequences. So let's have another look at that. So that's the average mean wind speed flowing through this canopy of trees. So here's a top view of it. And when we average spatially, let's average over wide, thin slabs, so we can preserve the vertical heterogeneity in the canopy, but smooth out plant-to-plant variations in the horizontal. And we usually denote that by an angle bracket. And when we do that, we find that we get two terms here. One is the average of all the front-back pressure differences on all the bits of plants which stick up through our little slab of air. And the other is the viscous drag on all the plant bits that stick through our slab of air. So these two things together are our aerodynamic drag term, but they're working on not the velocity we started with, but the area average velocity. So we've invented a new fluid, in a sense. We've invented a fluid which is like Darcy fluid in soil flow. It's the average flow, spatially average flow through this canopy. And some other terms appear, because just as in temporal turbulence, average fluctuations can combine because of nonlinearities in the flow equations to give you stresses. Now we can have spatial variations in the steady flow, and they also can combine under this operation of spatial averaging. And we call these dispersive fluxes. And it's sometimes called double averaging. You're averaging now in time, as Reynolds did and we've done ever since, but now we're averaging in space as well. Now, I should say that this came somewhat late to micrometeorology, starting with the paper by Wilson and Shaw, then a seminal paper by Mike Raupak and Roger Shaw in, I think, 82, was that? And then some more stuff where that was extended to volume averaging instead of spatial average, instead of area averaging. This double averaging was already quite familiar to chemical engineers, 10 or 15 years earlier than that. So in canopy turbulence, we need to keep track of two kinds of fluctuations, both the temporal fluctuations, but also the steady fluctuations as the earth finds its way around all these plants. And we usually denote these local variations in the average and the time mean flow by a double prime, whereas the variations in time around the steady flow by a single prime. But that allows us to define three forms of kinetic energy. Remember, we talked about shear and buoyancy producing turbulent kinetic energy, and then that turbulent kinetic energy ending up as heat, eventually through the action of viscosity on tiny eddies. But now we've got three forms of kinetic energy: the kinetic energy in the mean flow, the kinetic energy in the spatial fluctuations, and the kinetic energy in the temporal fluctuations in our slab. We can say a lot more about that, but probably only for those who are really interested in it. So interestingly enough then, when we look at the way that canopy turbulence from many, many different canopies collapses, if we use either the vorticity thickness, which I'll explain later, or the canopy height, as in this set of pictures, as scaling values, and U star as the velocity scale, then we get an incredibly good collapse from canopies which vary from 25-meter pine trees to some deciduous trees to wind tunnel models that high, and basically everything in between. So here we see the momentum flux, the UW, the downward flux of momentum from the wind into the canopy. It's pretty constant through the surface layer, and then it gets absorbed rapidly as drag on the plants, and none of it reaches the ground in these relatively dense canopies. The velocity profile itself has this characteristic inflection point as you go from a boundary layer profile to an exponential profile, and the variances of the streamwise and the vertical velocity have a relatively quite a strong height dependence as you get into the canopy. So it departs quite strongly from Monin-Obukhov conditions where these things are assumed to be constant above the ground. So how did we get those statistics, and how do we find this stuff out? Well, measurements in the canopy airspace usually involve towers. This is an experiment run by Ned Patton at a walnut orchard in California in 2011. This is probably the most detailed set of canopy measurements ever made, with many, many sonic anemometers. When we were trying to do this kind of stuff in the 80s and early 90s, we could only drool over having this many anemometers, not only to deploy, but actually anemometers that work, because in those days, you usually spent most of your time going up and down towers, fixing transducers which stopped working, and so on. Or it rained, and then you'd have to go up with plastic bags, put plastic bags over the sensors, or else it wouldn't work for the next 3 weeks. So we could measure profiles at different levels through the canopy and above. In a famous experiment at Camp Borden Pine Forest in Canada, in '89, Roger Shaw, with his student Gao and some others, measured time traces of temperature fluctuations from sonic anemometers at different levels in this pine forest. The top of the canopy is, where are we? Z upon H, so the labels on the traces are the height. So Z upon H equals 1 is the canopy top, then descending into the canopies, the bottom 4 profiles, 3 profiles, and 2 above, up to 2.5 times the canopy height, 2.4 times the canopy height. And if you follow those traces along, you could imagine the turbulence sort of moving along like a frozen, field of spatial turbulence. It isn't really. It evolves as it goes along. But if you like, you can think of, if you reverse time, as on the right-hand graph, you can think of that as space. So what you see if you look at that turbulence on those traces on the left is you can see, you can sort of line up what we call ramp structures. We'll have an increase in temperature, then the sudden drop, an increase in temperature, and a sudden drop, increase, sudden drop. And those ramps, those cliff faces, sort of extend right through the canopy. And this was a bit of a revelation at the time. Nobody had really seen physically the spatial extent of structures going through the canopy. Remember, people were thinking that canopy turbulence was little eddies being shed from leaves and branches. Now here we have a canopy where there are eddies which are clearly of canopy height or bigger. And if you then composite many of these things, and what they saw is if you take these fronts and take that as a trigger, so line up all the structures which have a trigger like that, then what you see is that rapid change is a so-called scalar microfront, a temperature microfront, a rapid change from warmer air in the canopy to cooler air coming into the canopy. And because we have these sonic anemometer traces, you can also look at what the wind vector is doing. So on this side, we see a movement upwards of warm air from the canopy, and we call that an ejection. It's upward movement of warm air. And then the scalar microfront followed by a sweep. A sweep is a very fast downward movement of fast air, and it's cool air because it comes from above. So this two-dimensional picture of ejection followed by a sweep is sort of the archetypal picture of canopy turbulence, which has been repeated over and over and over again in many different experiments. But it's hard to figure out three-dimensional structure of these eddies, which were doing, causing us to depart from Monin-Obukhov or produce ramp structures from just a single one-dimensional tower. So we did a series of experiments in wind tunnels where we could actually, because the flow is statistically stationary and repeatable, we can do many, many different positions with two sensors, and so build up a spatial pattern of the turbulence. We can do it in a different model canopy. This is, for obvious reasons, called the tombstone canopy. The reason that that looks like a tree canopy, as far as the wind's concerned, is, if you remember, we are assuming that the drag on the plants is mainly pressure drag, and so varies like u squared. Now, if you take the plants from a real canopy, scale them down geometrically to fit in the wind tunnel, they'd be so fine that almost all of the drag would be viscous drag, and it wouldn't behave like a real canopy does. So one of the things you do in the wind tunnel is abandon some of the geometric similarity in order to get aerodynamic similarity. You want the canopy to appear to the air like a real canopy. You're less concerned about it having individual leaves and so on. And now in more recent times, we can use three-dimensional laser Doppler anemometry, where we can actually track the return for when turbulence intensities in canopies are so high that often the wind is going backwards, and conventional sensors like hot wire anemometers can't tell the difference between the wind going one way or another because they depend on the cooling. But the LDAs, can actually resolve all three components of the velocity. And this is the latest incarnation of the tombstone canopy using 3D LDV. But the most revealing kind of things are now being produced by large eddy simulations. The reasons we don't have time to go into in these talks about why large eddy simulations of canopy flows actually are better simulations than standard boundary layer flows. But here we have two simulations, again by Ned Patton, of streamwise velocity at the top and scalar fluctuation at the bottom. And you can see on the bottom, you can see those scalar microfronts that were picked out on that Camp Borden picture, where the scalar is being compressed between sweeps, ejections in front, followed by a sweep behind. So recalling again, we've already seen this picture, and that's a bit of a reprise. The early days, we thought they were wakes. We showed that became clear that the canopy airspace is dominated by very large coherent eddies. Because these coherent eddies don't decrease in size as you get down towards the ground, you start departing from Monin-Obukhov similarity as you get near the canopy, because these eddies are more efficient. And we saw that picture, which is taken from spectrals. Now, we saw those individual plant part things. Now, the source sink turns for heat, humidity, CO2 depend on the mean, and as we'll see on Friday, the fluctuating concentrations in the canopy space. So we look at the temperature in a typical forest canopy. During the daytime, there's the top of the canopy, the sun's heat is mainly absorbed in the crown space, so we get a maximum in temperature there. And then the ground here is shaded, maybe evaporating a bit, so it's generally cooler. So the lower part of the canopy, below the crown space down to the ground, can often be stably stratified. You can get waves in there. Whereas the upper part of the canopy is strongly unstably stratified and very turbulent. At night, things reverse. The upper part of the canopy, the crown space, is radiating infrared radiation to the sky and cooling down, but the ground is a bit sheltered and stays warm. So down below, between the crown space and the ground, you get unstable stratification and buoyant turbulence, coupling the ground to the crown space, which then radiates that heat away to the sky. And we get these different profiles now of heat flux. During the day, the heat flux increases as we go up, as more and more leaves are involved in adding heat to the mixing, and then it's constant above. At night time, it's the other way around. The heat flux is downwards, warming, coming from the atmosphere to warm the canopy, which is cooling itself by radiating up into the sky. So that sets the environment for the individual leaves and plants and their energy balances, and we can write an equation for temperature, which has got these dispersive as well as eddy fluxes, and the source sink term. And that source sink term, as we showed, is now often parameterized by the leaf level temperature in a slab, very wide slab, to average out these leaf-to-leaf variations, and the average canopy temperature divided by a boundary layer resistance. And you can see from that that if everything is steady, so everything on the time rates of change and the advective terms, the spatial terms are zero, then there's a balance between the source or sink term and the gradient of flux in the canopy. So the flux divergence is exactly equal to the source sink terms. Now I'll finish with one last slide, which just to show you that things are always more complicated than you think. One of the consequences of having these large eddies in the plant canopy is that heat doesn't necessarily flow from the colder to the hotter. There were two English musical comedians in the 60s called Flanders and Swan, and they had a song, it's about the second law of thermodynamics, and if I remember, there were two lines that said, heat can't flow from the colder to the hotter. You can try it if you like, but you really better not to. And it goes on in that vein, unfortunately. But in a plant canopy, it turns out that heat can flow from the colder to the hotter. So this is a famous picture from an experiment by my colleagues Tom Denmead and Frank Bradley in Uriara Forest at Canberra in 1986. It's a pine plantation about 18 meters high. And what we found is that above the canopy, we have a decrease in temperature. Remember, the peak in temperature is in the crown space where the sun's radiation is mainly absorbed. And we get a decrease in temperature, so the heat's going from high temperature to low temperature, as it should do if God's in his universe and so on. But down below in the trunk space, where temperature is increasing with height, heat is still going up. If we look at water vapor, up here, the water vapor concentration is decreasing, the evaporation is upwards, the latent heat is upwards. Down here, there's no gradient in water vapor in concentration, but there's still a substantial upward flux of latent heat. And for CO2, the CO2 concentration is decreasing as you get into the crown space, where the plants are photosynthesizing like mad and decreasing the concentration. So the flux of CO2 is going from higher to lower concentrations, as it should. But down here, where we get this, we're actually getting respiration of CO2 from the soil. We get a reversal in the CO2 gradient, but still the CO2 flux is down because it's still being photosynthesized down here. So we have this failure of the eddy diffusivity concept in the plant canopy. The reason is that eddy diffusivities depend on the agency of transport, in this case eddy mixing, being of much smaller scale than the scale over which the mean gradients change. Now, because the mean gradients are set by the canopy scale, where the foliage is, but the eddies are set by an emergent process of the whole canopy, that condition is no longer met. And so you can no longer expect things that you've grown up with and loved all your life to actually work. And this kind of stuff was one of the, if you like, seminal pieces of work which turned our conception of plant canopy turbulence around. So just summarising all of that, turbulence atmospheric boundary layers necessary for life as we know it, Jim. The turbulence is a balance between shear production, as the geostrophic wind, as the wind flows from high to low pressure regions around the planet, is slowed by the drag of the surface, and of buoyancy, which is positive when the sun's warming the ground and negative when the ground's radiating its heat away at night. And ultimately, it all ends up as heat. We can use dimensional analysis to show the domination of buoyancy in the daytime boundary layers as soon as you get away from near the surface, and a mix of shear and buoyancy in the lowest 100 meters. And that Monin-Obukhov similarity theory works quite well in the lowest 100 meters as long as you don't get too close to the canopy. Then it doesn't work. So now you get roughness sublayer theory, which takes account of the fact that the eddies that are doing the transport stop decreasing in size, but it depends on a new length scale called the vorticity thickness. And that reflects this more efficient turbulent mixing. In the canopy, all the transport and the turbulent kinetic energy is dominated by these large eddies. They're not connected to individual leaves, but they're connected to the fact that the canopy as a whole absorbs momentum. So the overall environment of the canopy airspace is a balance then between energy, momentum, and carbon exchange at individual leaves, and these emergent large eddies that dominate the turbulence environment. So it's best to think of the canopy as a complex system, where these emergent properties, the large eddies, set the environment for the multi-scale interactions between leaves and the airspace. And in turn, that set the evolutionary stage in which plant development and function has evolved. So on Friday, we'll talk about, and there'll be more pictures and fewer equations, what's the origin of these canopy large eddies? Why do we call them emergent properties? And how does the canopy talk to the whole atmospheric boundary layer above? And how does the atmospheric boundary layer, in fact, imprint itself on the way that plants behave right down at leaf scale? Okay.